Hi, everyone. This is Alex from NEAR. With me today is John Adler, Chief Researcher and the co-founder of Lazy Ledger. We will talk about Lazy Ledger today. And John, would you like to introduce yourself and give us an overview of what Lazy Ledger is and technology behind it?
Sure, yeah. So as you said, I'm the Chief Research Officer at Lazy Ledger, and I'm a co-founder. So I do protocol specification and applied research. So I guess I can start with, I'll move this over, and I guess I can start with kind of a brief overview of what Lazy Ledger does, and then we can start talking kind of about the techniques we use to get there. So Lazy Ledger is essentially a blockchain that is specifically designed and optimized just for data availability throughput. It doesn't do any execution at the base layer. Rather, it just orders messages, in other words, just zeros and ones. It just orders them through the consensus mechanism, and then applications can run on top of Lazy Ledger and execute over the ordered messages. Okay, are we ready to start talking about the fundamentals?
Yes, absolutely.
Great. Yeah, so this is kind of a terribly drawn blockchain. We all know, what the blockchain does. Each block header points to the previous block. And let's see if we can draw with the pencil. And each block is composed of two parts. So here is the block header. So this is the header. And this is the body. And the body consists of a list of transactions. Transaction 1, transaction 2, and so on, right? In some order. Usually, it's going to be in some topological order. Some other blockchains have proposed other things like lexical ordering and stuff. But there's going to be some ordering there of these transactions, and there's going to be a block header. And the block header usually consists of a pointer to the previous block, and it'll have a root of transactions and a root of the state. So let's kind of add some text here. So this one here is going to be a transactions root, and here you're going to have a state root. And the text is tiny. I don't know is that big enough, or do you want me to make it bigger?
Let's make it bigger. I think bigger will be better.
Size. Bigger. Is that better?
Yes.
Transactions root. Way better. That makes this bigger. State root. Here's your body. And this over here is your block header. Great. I don't know, how do you move things?
I use this select tool, V.
I see. Okay. This is starting to make sense. Great. So this is the state root, and this is the transactions root over here, right? And every block header has this. Now, there might be some other roots in there. There might be a root of receipts. There might be some proof of work nonce. There might be a list or a root of votes if you're using a proof of stake style protocol. But those are kind of not relevant to what we're going to discuss here. So in a normal blockchain, what'll happen is you run a full node, and the full node fully executes every single transaction in the block body. Okay, it goes through the transactions one after the other, and it fully executes them. And then it makes sure that the transactions in here match up with the transactions root, and then make sure that the computed state at the end of the block matches up with the state root. So it's fairly straightforward. And let's pretend that you have an attacker. So an attacker will create a longer chain of blocks. Arrow. Forgive my very uneven arrows, but hopefully that'll suffice. So let's undo this. This block should come from let's say there's a block over here. There's a block over here, right? So the attacker, forks off of over here somewhere, and he creates a longer chain of blocks. So the attacker has more than 51% or more than 50% of the hash rate. If all of these blocks are valid, then the full nodes will follow this as the longest chain, right? They'll do a reorganization. They'll follow this the longest chain. Now there's things that might happen there. Penalties might be enforced. Some people might decide the coin price should drop, or the cost of the price of the hashing hardware should drop, stuff like that. That's not really too important to our discussion here, but the way the consensus protocol works is they'll just follow the longest chain. So if all of these blocks are valid, the full nodes are going to follow this, and the light nodes will also follow this chain, right? Light nodes just check the proof of work, so they just follow the longest chain, and they don't validate transactions in the block body. Okay, so now this is where things get interesting. What happens if, let's see if we can draw with a different color. Let's use red. Right, so there's some transaction in here that's invalid. The miner decides to insert, these colluding miners that have, more than 50% of the hash rate. They decide they're going to insert a transaction there that, gives them a whole bunch of coins, like let's say 1 billion bitcoins, something like that. Right, and so there's obviously an invalid transaction. You can't have a transaction that has 1 billion bitcoins, but they do it. So full nodes will reject this fork here, obviously, because this is an invalid transaction. And full nodes will follow the longest valid chain, not the longest chain. But light nodes will still follow this chain. Because light nodes just follow the longest chain. They don't care about transaction validity. Right, so the light nodes will follow this chain. So now you see that there is a problem, because if many users run light nodes, and only a few users run full nodes, that means the light nodes can be tricked by this attack, which is especially dangerous. So the reason that Bitcoiners and the Bitcoin philosophy is everyone should run a full node is because of an attack like this. Is that everyone who isn't running a full node could end up getting tricked, and if all those people get tricked, they could still continue using Bitcoin, and we don't really have a way of enforcing a penalty to the miners that have done this reorg. Right, like the miners could just do a reorg, and then if the price of Bitcoin doesn't drop, if the hashing hardware or if the hash function doesn't get changed in response to this attack, then the miners have just executed an attack, and there's no penalty for it. There's no cost to the attack, so this means they would be able to attack Bitcoin anytime they wanted for free, which would obviously be a terrible conclusion. So this is why they encourage everyone to run a full node, because Bitcoin doesn't have a way of protecting against this. So can we do better? Do we have a way of protecting light nodes from this kind of attack? And the answer is yes, in 2 steps. So we'll cover the first step. The first step is fraud proofs. So let's see if I can.
So before we dive in, for me to understand the without an ability to insert an invalid transaction, right? Or I guess in more general sense, it is not just an invalid transaction. It could be that all the transactions are valid, right? But the state root does not correspond to the output of them, right?
That would be data. That would be like a block withholding.
No, what I mean is that the block, like let's say the block contains 10 valid transactions, the state root is incorrect, then the full node would also reject it, right? They will validate it.
Yeah.
But the light client will still accept it, right?
Yes.
So the miners, they can attack the previous attack you described with the longest chain does not contain invalid transactions. This is still a valid attack that the miners can execute, right?
Yeah, I said transactions, but it really should have transactions plus the state root, because the state root defines the state, and transactions just modify the state. So instead of having an invalid transaction, they can just directly modify the state in an invalid way by just changing the state root at the end. So yes.
Right. But my question is more of so let's say everybody's running full node, right? The attacker, which has 51% of hash power, can still attack the attack you described first, right? They will create a longer chain, and they will double spend, for example.
Oh yeah, they can still do that. So fraud proofs don't protect against that.
Yes. So we have effectively we're saying that the attack with an invalid state transition is way more dangerous because it allows you to apply state transitions which are completely invalid, while the longer chain or like reorg attacks, while they're still dangerous, they're less dangerous because it is still only valid transactions that can go through. Is it the idea, or why we're thinking that?
Yeah. So the reason is that we want to move beyond the model of everyone has to run a full node for the system to be secure. That's essentially what we want to move beyond. If let's say 99% of Bitcoin users and traders and investors and everyone involved in Bitcoin ran SPV nodes, ran light nodes, if someone attacked the system, the full nodes wouldn't have any way of proving that an invalid transaction was included in a Bitcoin block to any of those people. So the Bitcoin economy would just continue. So the attacker essentially has minted himself a bunch of Bitcoins for free.
Right.
And they can do this whenever they want. So we need a compact way for people who are running light nodes to have some sort of guarantee of block validity.
Okay,
Does that make sense? Yeah.
Yes. Let's dive in.
Yeah.
How we do
So now let's see. How do I? Okay, there we go. So I'll push this up. Line. So line, which is red. Okay, so the first thing we need is one, fraud proofs, and I'm going to talk about specifically the state transition fraud proofs. There's one other scheme for the UTXO data model, but for here we're going to talk about the state transition fraud proofs. Okay, so how do they work? So we have our blockchain again. We have arrows, and then we have again our block headers. Right. So our block headers have, in here they have the state root. Here's another state root, right? And again, the state root commits to, or it's the Merkle root of the state tree. State trees can be represented in multiple ways. In Ethereum, you have the Merkle-Patricia tree. Other systems have a sparse Merkle tree, and so on. But it's essentially just the root of the state. And we want to make sure that we want to have a way of proving that the state root of, say, the next block, or let's say the state root of this block here, the state root of the next block. We want to prove that this is invalid, assuming the previous one is valid, right? So let's draw some check marks. So this one here, the state root is good, and this one here, the state root is bad, right? So they do an attack by either inserting an invalid transaction, or the state root is just invalid, and they've just given themselves 1 billion coins in the state. They just and inserted that as a leaf in the state. Right, so this is the kind of thing that we want to prove. By induction, this is sufficient because we always know the state root at the genesis block. So as long as you can show this for one step, then by induction you can do this anytime you want. So how would we do this? Let's see. Pencil. So this block has a bunch of transactions. So we know that if we start at this state root here and we execute these transactions, if this state root is not what we get, then that means this block is invalid in some way. Do we agree?
Yes.
Great. So the obvious naive way is saying, well, just give someone a block and they just execute all the transactions and compare the state roots, right? They have a pre-state, and then there's a post-state, and the post-state that's committed to here in this block doesn't match up with the post state they compute, then that's an invalid block, right? There's your fraud proof. So this is kind of the naive way of doing a fraud proof.
But they don't have a pre-state, right? A light node does not have the state.
Oh yeah. So the light node is given the pre-state root over here, right? So in order for the light node to know, in order for the light node to be able to execute these transactions, the only thing it needs to know is the pre-state that is touched. It doesn't need to know the entire pre-state. Right? So the first thing that you give, which is thank you for bringing that up. Let's see. So what you need to give to the light node. So the light node has previous state root. It's also given Merkle branches to previous state elements that are touched. And it's given it's given it's given the entire block, so it's given the post state root, and all the transactions. I'm using Markdown here with ones. Okay, and it's given the transactions, right? In the naive case, and then if the Merkle branches aren't sufficient, then as it executes a transaction, it's going to say, well, I'm touching a state that isn't part of these Merkle branches. The proof you've given to me is insufficient, right? So that means it's not a good proof. right? So if it executes all the transactions successfully, and then the Merkle branches are sufficient, then at least the fraud proof itself is correct. You don't know if it's correctly formatted. Okay, so essentially what you're doing is you run through all the transactions and you check to make sure is this post date route different. So this works, but there's an issue. What's the issue?
Well, it's heavy.
Well, yeah, it's heavy because you have to execute every single transaction, right?
Right. Well, I
Like,
guess the other issue is that we don't have the access to transactions.
You what?
We might not have access to the transactions themselves.
That's part two. So in this case, let's assume that they have full access to the transactions.
I see.
Okay, so
That's
which is a good thing,
then, right?
So this works, but the problem is that, as you said, it's heavy. Executing all the transactions could be expensive, especially in a resource-constrained environment like a blockchain, right? So can we do better? The answer is yes. So draw a line. Draw a line. So can we do better? The answer is yes. So what we do is, let's see, pencil. So here's our, I can write. Here's our transaction route. Right, it's the Merkle tree of some transactions, right? So here's transaction 1, here's transaction n, right? There's a bunch of transactions in between. Dots. So what we do is we say, well, what happens if after this transaction, I also put inside this tree, I just put some intermediate state root. And let's see, how do I select? Select. Let's move this over here. Yeah, so after every single transaction, I'm going to insert an intermediate state root. This is the naive way. You don't have to do it after every transaction. It could be after some parameter number of transactions. It could be after a certain amount of gas. But naive case, we say after every transaction. So intermediate state root n. Right, and then you commit to this into a tree. So instead of a transactions root, now you have a data root. So this is a root of where the leaves are, transaction, then the intermediate state root after executing this transaction, then the next transaction, then the intermediate state root after executing that one, and so on. Right? And intuitively that makes sense because each transaction is a state transition, and a block is a group of state transitions. So when we're doing this naive fraud proof over here, let me fix this typo. But when we're doing this naive fraud proof, we're essentially doing a state transition fraud proof, but over a block. Right? We're saying here's the previous state root, here's the next state root, execute a bunch of state transitions, and then the state roots at the end should not match up. So we can do the same thing. We include a state root after every transaction, and then we do the same process, but instead of executing all the transactions in a block, you just execute one transaction. Does that make sense?
Yeah, that makes perfect sense.
Yeah. So and then you give exactly what you give here, except instead of a list of transactions, you just give one transaction, right? And then again, you just run the transaction through. So this is one. Is there an eraser? Erase. Let's erase this. Yeah. So this is how you do fraud proofs. So now you brought up a very good point, which is what happens if these transactions here? What happens if the majority miners just hide them? What happens if they just don't show them to anyone? Right? They show the block headers, so the block headers are still being sent out, and light nodes will still follow the block headers, but no one can actually construct this fraud proof because no one knows what's inside the block, right? And in fact, they don't even know if it's invalid. It could be a valid block, it's just hidden, right? So how do we deal with this? And this is where the more involved data availability proofs come in, which is where we're going to probably spend a bit more time. And the existence of data availability proofs is something that the Bitcoin research community has generally considered not possible, and that's why they didn't consider fraud proofs possible, exactly because of the problem of data withholding. But they are possible with pretty decent guarantees with pretty weak assumptions, which is what we're going to discuss here. So data availability proofs. So this is the data availability proof scheme that was formalized by Mustafa Al-Bassam and Alberto Sassini, I think, and Vitaly Buterin in a paper, I think it's around September 2018, or yeah, so I think around September 2018 or October 2018, somewhere around there. So it's been but the idea of doing these fraud and data availability proofs less formally has been around for a bit longer. So this is the scheme that we're going to be using at Lazy Ledger. It's also the scheme that is used for Serenity, or that has been proposed for Serenity. So how does it work? So let's start with kind of the most naive way. So this one here is going to be like a straw man, the most naive way, right? Straw man data availability scheme, right? So this is like as naive as you can imagine. So what we're going to say is, let's draw a rectangle. Let's take the block, right? Let's say this is the block. I'm gonna draw it out in a nice rectangle so that we can chunk it up and stuff. Okay, so let's say I chunk it up into 8 pieces, like so. Is there a way for me to copy this by any chance?
Let's see.
Select. Ah, I can copy.
Nice.
Paste. This will come in. This will be useful. Let's put this over. Let's put this over here. I'll need this later. Okay. So let's consider this to be our block. So the you have all the block headers, but you don't have the block bodies, right? So let's consider this to be the block body, right, of one of our blocks. So what you could do is you can say, well, I'm going to let's use blue. Blue is a good color, right? Let's say I'm going to randomly sample. Like I'm a light node, not a full. This doesn't really apply to full nodes again, because full nodes fully download blocks, right? They don't have a problem with data withholding. If they see a block doesn't have a block body, then they say, okay, there's an invalid block, I reject it. So this is really only for the purposes of light nodes, right? So how can a light node convince itself that the data is available? So well, the light node can say, well, I don't want to download the full block because that would make me a full node. So what I'm going to do is I'm going to download just a small portion of the block, right? And let's say there's 8 transactions in this block, right? If there are 8 transactions in this block, and let's say the node randomly samples 3, the light node, right? So it's going to sample this one, and let's say this one, and then this one, right? Right? It just randomly samples 3. This is the naive case, right? But now what happens if the attacker, let's say there's a guy here with horns because he's an attacker, right? The attacker hides just this one transaction, right? If he hides just this one transaction, then a light node that does this data availability check has convinced itself, yes, okay, I checked these 3 transactions, I've been given them, they're valid, they seem to be valid transactions, right? Therefore, I assume the block data is available, right? And other light nodes do this too. The chance that a light node asks for this one transaction and doesn't get it because the hacker is trying to hide this, the chance that it lands on this would be 3 out of 8 or whatever, right? Which is in this case we're using a very large number. It's like you're sampling half the block, but imagine that you sample let's say it's 1,000 transactions and you sample 5, right? Then in that case you can see the probability that a light node finds that this thing here is being hidden is very, very small, right? So this is not a great scheme because the attacker they only need to hide one transaction. In fact, they only need to hide one byte, right? They just need to hide one thing, and then the entire block you can if it's hidden, then you can't show that you can't show that this transaction is invalid if it's hidden, if you don't know what the transaction is, right? You can't construct one of these state transition fraud proofs because one of the point of the fraud proofs is you need to execute a transaction. If the transaction is hidden, you can't execute it. So this this generally is not a great scheme because the chance that a light node will actually find out that this block or that part of this block is hidden is very, very small. So we want something better. So how how do we do it? Let's do B. Let's use erasure coding. And again, we'll make this naive. Or I guess I could say, we can say 1D. Well, 1D naive. Right. So let me scoot this over a bit. Let me copy this, because we'll need it again. And move this here. Okay. So what we're going to do now is we're going to use erasure coding. So the way erasure coding essentially works is that it uses math, which we're not going to cover here, but essentially you can think of it like, let's say these 4 are the original data that I have, just these 4. What I can do is I can actually compute some parity shares. So here's my original data. Original data, and here's the parity. So I'm given this original data. I'll compute some parity data, and how much parity data you get is dependent on some parameter. You can change this. It doesn't. In this case, as you can see, it's 1-to-1. It doesn't have to be 1-to-1. It can be different. But essentially, you have this original and parity data now, right? So as you can see, you're getting more data. So this is bigger. The original data is four chunks. The parity data is also 4 chunks. So in total, you have 8 chunks. And depending on your parameter choice, essentially what this gives you is, if you can recover 4 chunks out of these 8, any 4, you can recover the original data. And of course, you can also recover the parity data because you just recompute the parity data. Right. So this seems like it's kind of solves our problem, because now you no longer have the problem. You no longer have the problem of the strawman scheme up here. The strawman scheme again is that an attacker could just hide one of these chunks over here, one of these transactions, and you would have to, the light node would have to specifically request that transaction, right? Otherwise, it wouldn't know that something is being hidden. In this case, if you have this, let's say you have this example where you have 4 and 4. How many of these chunks does an attacker have to hide to be able to hide the block?
Yeah, they need to hide 5.
They need to hide 5, right? If they hide 3, it doesn't matter which 3 they hide. If they still broadcast the other 5, then, or let's say they even hide 4, and they broadcast the other 4, it doesn't matter which 4 they broadcast, the entire block can be reconstructed, right? The original data can be reconstructed, and from there we can also recompute the parity data, so the entire thing. So they need to hide more than half. In the symbol example, it's 5, right? So we're going to draw that out. Let's say in red, right? So an attacker hides 5, right? An attacker hides these 5 shares, right? And I didn't draw that properly. Let's undo this. Yeah, so an attacker hides 1, 2, 3, 5, like this. Yeah, that's better. Right, so an attacker hides 5. They broadcast out the other 3, right? Now here's kind of where some of assumptions come into place. So one thing that's important is we assume that there's at least one honest full node in the network that the light nodes can connect to, and we assume that they can communicate with each other, so there's no eclipse attack. The reason this is important is that if the light nodes and the full nodes can't talk to each other, then the full node can't even construct a fraud proof, right? So the light node sample stuff, but there's no fraud proof or anything, then what are you doing, right? So we do make that network assumption. So what this means is essentially, if the attacker broadcasts out any share, we assume that the entire network is eventually going to hear of that share. It might take a bit of work, but we assume that the entire honest network will eventually hear of that share, right? So they can't they can't hide say like these 2 over here for one full node, and then these 3 for the other full node, and then for another full node hide these 5. They very much have to hide the same 5, right? Okay, so we have this construction. So now a light node comes along, and the light node does some samples, right? So the first time it samples, it will get tricked that the data is available if it lands on an available chunk, right? Like if a light node samples this chunk here, then it says, okay, that chunk is available. I've been given it, right? I guess one thing to make clear is this this erasure coded version of the chunks of original and parity data gets committed to in the block header. So
with the Merkle proof, right?
Yeah, there's a Merkle root. So we Merkleize this. Obviously, if you just have the data floating around, then light node samples, it doesn't know what it's sampling, right? So okay, so when a light node samples this chunk here, it has to get a Merkle proof from the block header to the chunk, just so we're clear. Okay, so if a light node samples this chunk, it says, okay, this chunk is available. So if it stops there, then it would be convinced that the block is available and it would have gotten tricked, right? So the first time it samples, what's the approximate probability that it got tricked?
It will get tricked with the 3/8, right?
Yeah, sure. Sure. Well, let's simplify that a bit.
Well, then parity minus 1 over total number.
Let's assume, yeah, parity minus 1 over total. Let's assume that the large number of chunks. It'll be approximately.
Yeah, then one half.
Yeah, 1/2, right? Because it's we assume a large number of chunks. Great. So round one. Round one, you have the probability p is approximately half, right? Okay. So now it does a second round of sampling because you don't stop there. One round of sampling is pretty terrible. So it does a second round of sampling without replacement. So what's the approximate probability that it has gotten tricked?
After k rounds, it's going to be 1 over 2 to the k, right?
Yeah. So it's 1/4 with around n or k. Well, sure. P is 1 over 2 to the k. You can say, right? So as you can see, the probability of it getting tricked decreases exponentially. So you don't. And one thing that's interesting to note here, this probability decreasing of getting tricked, is it in any way related to the number of chunks?
It is it is important that parity is 1-to-1 with the original data, right?
Oh yeah.
But
yeah,
other than that,
we assume the parameters, the system parameters set up that the parity and original data are 1-to-1. Yeah.
Yes. Well, there are a couple of things. So one is, if you assume that the number is sufficiently large, right? So 1 second is a good estimate, then it should be independent of the number of chunks. But also, I guess something we didn't touch on is we assume that the adversary decides on what to reveal in advance, right? Which I guess it doesn't have to.
Well, again, is that we assume that the network is set up that if a chunk is distributed to an honest full node, it will get distributed to all honest full nodes eventually.
Right, but if I'm a light node, right, and I'm sampling, and I just happen to be connected to several non-honest nodes, right, I will sample, I will start sampling, and the adversary, as they receive my request for a share, they will decide to reveal it, right? Or we're assuming that
we assume that the light nodes are connected to a full node, an honest full node.
I see, and we're also saying that if the so then I guess what is not one assumption we did not discuss is so let's say I'm a light client, I'm a light node, I'm connected to, let's say, 12 full nodes, right? So I chose to sample a particular share, and I chose a particular full node to sample it from. So if I fail to sample it from it, what do I say? Do I say that the data is unavailable, or do I try to sample from another full node?
You continue trying until some parameterizable timeout.
Right. So therefore, if I'm connected to any full node which is controlled by adversary, eventually I will sample all my shares from that adversarial node, right? And so adversary can choose to specifically.
Sure, but the shares. Well, we assume the light nodes aren't under Eclipse attack. If they're connected to at least one honest full node, then they're not under an Eclipse attack.
Right, but in this case, I'm saying, let's say I'm connected to exactly one malicious node, and everybody else I'm connected to is a full node which is honest, right? Yeah. So I'm saying I want to sample. Let's say the parameter is 5. I want to sample five shares out of 1,000, right? So I go to the full nodes, and the full, and let's say that the. So the way I see it is adversary first sends me the hash of the block, right?
Yep.
So at this point, from someone I heard that the block exists. Other full nodes haven't heard about it yet. So I start sampling the shares, and all other full nodes tell me, well, I don't know the block. I'm not going to tell you the share. So I keep on trying, and I end up trying to download it from the malicious node. And malicious node at that point decides, for the first time to reveal the particular share, right? So maybe it will not be able to check all the light clients because all the light clients collectively will probably hit all the shares, but it will be able to check one particular one. So let's say it wants to check Coinbase, right? So the specific in our Coinbase is Coinbase goes and samples, and ultimately Coinbase ends up sampling from the adversary, and adversary reveals specifically the shares Coinbase wants to see.
So we also assume a network model where queries can be made anonymously.
I see.
As in you can't associate who is making the query. In practice, the reason that this is an okay assumption, even if we don't use things like Tor and whatnot, is that say Coinbase, they can run 2 full nodes, or they can run 100 full nodes, and you might know 1 full node is Coinbase's, but you don't know all of them are operated by a single entity.
Yeah. Well,
like
in this
behind
case,
the
it's a light
scenes.
client, right? We're checking the light client. So I guess Coinbase will not be running a light client.
Well, they
right?
wouldn't be running a light client, right?
Yes.
But like an end user, it's like an end user. Okay, they run one light client, but how do you know they're not running 2 light clients, one on their phone and one on their computer, that belong to the same person? The 2 nodes can communicate with each other off chain, and you know the human is essentially a very good way of having private communication between 2 computers, right? Like you can't really. It's pretty hard for a computer to spy on human typing on a keyboard here and then typing on a keyboard there.
Yep. Okay, so with those assumptions, because I see you have the third one drawn, right? So we are about to find out something bad about this model. So it's not at all obvious to me what is wrong with it with the assumptions we discussed. So I'm excited to hear what is it.
We will, because this is anyway. Yeah. So there's kind of a few interesting things to note. The chance that a light node can be tricked is completely independent of the block size. What this means is the number of rounds you need to do is constant. It is not big O of n, where n is the block size. It's not big O of some function of n. It's big O of 1 with respect to the number of transactions in the block, or the number of bytes, the number of gas, whatever you want, right? This is constant, which is pretty amazing because it means that you just have to do a constant number of samples, and each of these sampling operations is logarithmic in the size of the block, because it's a Merkle branch to the particular share, right? So this is a very, very cheap operation, which is great. But now here's kind of where the problem is. Let's say I have 1 light node, right? I have 1 light node. The light node samples 3 shares, right? Well, this example is bad because the number of shares is pretty small, right? Let's say the light node samples 2 shares. Just again, this is the small number, so it makes things a little disproportionate. But let's say the light node samples 2 shares, right? So let's say pencil. Let's use green, right? So let's say the light node samples this share, right? And in fact, the light node could sample this share, right? Okay, you just have 1 light node. I realize green is a terrible color choice because maybe a non-trivial number of our viewers are red-green colorblind, but these X's here are green. So the light node samples these 2 shares, just as light node, and there's not a single other node in the network. Let's say, right? Or this could be the full node, right? Because we assume there's one on its full node. So the full node tries its best to, by asking the network and everyone around, the full node tries to reconstruct the whole data somehow. If it can't directly download the original data, it has to ask the network for the shares individually, but it should be able to reconstruct the block. So let's say this full node is out there making requests, and it downloads these two. So this is what it gets. Can we reconstruct the block using only these 2 shares?
No.
No, right? Because you need 4 shares. Yeah. So the problem is that even if we fix this, let's say we set our k to 2 at some fixed number. Okay, so you have one, a light client or a full node or whatever. They download these 2. There's no guarantee that you'll be able to reconstruct a block if only 1 client does these requests, right?
Right, but wouldn't full node? The full node will try to fetch all the shares, right?
Yes, the full node will try to fetch all the shares. Yes, right. But the problem is, okay, the full node does, but the full node can't really prove to a light client that it hasn't been able to fetch all the shares.
Right, but So the way I see it so far is that the block would either be available, meaning that it did broadcast. So effectively, let's go through the timeline, right? So the block was published for the first time. Because we assume that if some message was sent over the network, it will eventually reach everybody. So eventually everybody learned that the block was at least announced, meaning that the header was announced.
Yes.
So after that, everybody will attempt to sample some shares. And again, we're saying that if some share was published on the network, eventually everybody who tried to sample it will be able to sample to receive it. Right? So with this assumption, it seems to me that with a sufficiently large K, for every available block, every light client and every full node in the system will know that it's available. And moreover, the full nodes will actually reconstruct it because full node will attempt to fetch all the
So
shares.
they can convince themselves it's available, but there's a problem. You might not be able to reconstruct the original data, right? And this is very nice. This is like strawman example. Let's say you have exactly one node that's doing these sampling, right?
I see.
The sample these two shares.
One node, yes.
Right?
But even then, is this node a light client or a full client?
It doesn't really matter.
Because if it's a full client, it will not try to fetch K shares. It will try to fetch all the shares, right?
The full node will try to fetch all of them. Okay, so let's say it's a light client, right?
But if it's a light client, then there is not a single honest full node in the system.
No, the full node is still honest. It's trying to do its job, but it can't. So there's another assumption here. The reason it's confusing is because there's another assumption, which is what we're going to talk about. So let's say one honest full node is trying to do its work, and you have one light client. The light client samples these two shares. It sees they're available, and these are the only two shares that are distributed, right?
But sorry for interruption, but consider the following model, right? Let's say that the full client will not distribute any shares until it has the full block. Right. So if the full node does not have full block,
the full node should still distribute shares, even if it's only seeing a few of them.
Right. Yeah, right. And in the model, but let's say we're changing the model, right? We're saying the full node will not be distributing shares until it has the full block.
Oh no, but that would be terrible because then full nodes would never be able to reconstruct the block unless they've been given a full block. So full nodes can obviously gossip individual shares.
The full nodes can gossip individual shares.
Like if the only way a full node would be able to broadcast anything outwards is if it received a full block, that means an attacker could just not ever show a full block and only do only give out individual shares, and then full nodes would never send an outgoing message.
Right.
So obviously,
so of course you cannot break every it will not be a productive time if you will be breaking every my model. So let's do the last one, and then we will proceed with the
So
let's say full nodes always send. They re-gossip to other full nodes, but they would not respond to light clients unless they have all the shares.
Oh no, they can also respond to light clients too.
Right, but I'm saying how will it break? Right. So
I think the reason is that the assumption seems very obvious. So can I go through the assumption?
Yes.
And then when I say it, it'll seem very obvious because obviously this happens in practice. So the attack is very contrived, but it's still an assumption that we have to make because we have to make all our assumptions. Let's assume there's one full node and there's one light client. The light client samples these two shares. This is bad. I shouldn't put this here. I should let's say sample this share, and then let's erase this, just so we don't get confused. The light client samples these two shares. It sees that these two shares are available, right? And let's say this is an imaginary world. There's one light client, samples these two shares. They're available, right? And then the full node tries to reconstruct the block, also seeing the full node can also only see these two shares, but the light client is convinced that the block is available, but the full node can't reconstruct the block, right? And that's the problem.
Right.
But now what happens if we have 100 light clients? 100 light clients each sample two, so maybe one samples these two, one samples these two, one samples these two, and so on. And then if the block isn't being hidden, then a full node can reconstruct it by asking around for the shares, right? So the trick is we assume there's a minimum number of light clients that are making these requests.
I see.
And those numbers can be fairly small. The paper gives numbers, I think, around 100 or something. So it's a very weak assumption. Obviously, in practice, for any reasonably sized network, you're going to have 100 nodes, right? Especially light nodes. So this isn't a very strong assumption, but it is something that we have to point out is that you do need a certain number of nodes proportional to the block size doing this random sampling. Does that make sense?
Yes, that makes sense.
So that's why it's confusing, is because it is kind of a contrived thing that doesn't really happen in practice. So assumption here, assumption, some number of light nodes, and we note that this is going to be proportional to block size, right?
Right. And so is it specifically the number of light client nodes, or is it the number of light or full nodes which are honest in the network? So let's say I have that many full nodes, but not a single light client. Will it work, or we specifically need that many light clients?
If you have this number of full nodes also they can pretend to be light clients and do
Right.
these requests.
Yes.
So sure, the number of nodes.
Makes sense.
We can simplify this to like number of nodes, really.
Cool. Number of honest nodes.
Oh yeah, of course, yeah. This is honest. Number of honest nodes.
Cool.
Yeah. Okay, great. So now, why doesn't this work? Why is this an age game? Also, it seems to be we're running a bit out of time from the schedule. Is that an issue?
No, that's not an issue.
Okay, perfect. I have some time. So, so what's the issue? The issue is, if this is erasure coded correctly, then we can do all this. But what happens if this is not erasure coded correctly? What happens if the block producer just doesn't? They either don't erasure code it correctly, or they commit to something incorrect. Because again, this has to be committed to in some Merkle root. But you Merkleize all these shares. What happens if they just don't commit to it correctly? In that case, you can't do that. You can't do this, right?
Right.
Or rather, it's like, even if you do this and the block is available, you might not be able to reconstruct the data nicely. So what you have to do is, if the erasure coding is incorrect, you need a fraud proof. So how do I prove that these parity shares are not correct based on the original data? How would I prove that?
So here you would have to share at least 4 shares, right?
Let's assume that they can reconstruct the data. Yeah, let's assume that they reconstruct the data. So a full node reconstructs the whole thing, right?
Or I'm saying the proof would have to be the size of the number of parity shares, right?
Yes, right.
So
the proof is essentially the proof is essentially you give the entire original data and you give the parity shares, right? Or you give the Merkle root and the original data, or 4 of these, right? And then you just say, okay, compute the parity shares, and then you'll see that the Merkle root doesn't match up. So the problem is that a fraud proof of this, that this is being computed incorrectly, is the whole data, which is exactly this is basically saying just download the full block, and then you can see that the data that the parity shares haven't been computed correctly, which is exactly what we're trying to avoid, right? We're trying to avoid having to download the whole block, because light nodes are resource constrained. So what do we do? So this is where the 2D scheme comes in. So see, this is erasure coding 2D. So this, I realized that this thing here is probably not useful anymore, so I can probably erase it.
We can replicate it 7 times.
I could, but it would still look. It would probably be way too big. So let's do a smaller table. Let's do like, oops. Let's drag this down. Okay. Let's do a square, and then some lines. And this is it. So what we're going to do is we're going to arrange our original data in rows and columns. So instead of being just like a single list, a single array, we're going to arrange it in rows and columns. So this thing here is our original data, right? So what we're going to do is, for each row, we're going to compute the parity shares for that row. So we extend it this way, right? So here's the parity shares off this row. And there's supposed to be lines here, but I'll not draw them for simplicity. All right, so again, for this row, we compute the parity shares and so on. Now for each column, we're also going to compute the parity shares of this column. This, right? And then you can do this, this third square if you copy one of these two, or if you compute parity shares this way, it doesn't really matter, right? Just this is kind of an implementation detail, but this is also going to be some sort of parity shares, right?
So I think what is important mentioning here, which is obvious for people with a background in math, but it is not as obvious otherwise, is that it doesn't matter how you compute this fourth square, whether you erasure code columns or erasure code rows, you will get the same values, right?
Yeah.
So like a particular value, yeah.
Yeah.
So that is not immediately obvious. I guess it requires understanding of some math behind.
Yeah, but like
Cool.
ultimately, this doesn't matter. What really matters is that as long as everything is a parity in some way, then that's all that matters.
Mhm.
Yeah. So even if it were different, it wouldn't matter. Just it's, you just say this is the direction I choose essentially. So this is your original data. So we note that the 1D scheme, our parity shares are twice as big as our original data, right? Here,
Yes.
our parity shares are 3 times as big as our original data. Right, so each of the side here is like square root of block size, square root of block size. So the length of this big square would be 2 square root of block size and 2 square root of block size, right? So let's type this out. So this one here is this one is square root n. Let's say n is our block size, right? This one here is also square root n. This is also square root n, and this one here is also square root of n. Right, so in total, the length of these things is 2 square root of n. And then what we're going to do is we're going to commit to a Merkle root for each row and each column. So in total, so with this one here, we just need one Merkle root. Right? We just take these and we just Merkleize them, right? So one Merkle root. Here we need a Merkle root for each row and each column. So in total, our commitment here is going to be 2 times 2 times 2 square root of n, right? Because this is 2 square root of n, and then we have 2 of these, right? So in total it's 4 square root of n. Whoops. 4 square root of n. So this is our commitment size. So this one here needs to go into the block header. Now we can have like a super compact commitment where you Merkleize this. So you can kind of represent it as like a two in 2 stages. But ultimately, nodes that want to do these data availability checks need to download this 4 square root of n commitment or commitments. So what this means is that this does increase the size of the block header. It means that now the block header has some overhead that's proportional to the square root of the block size, as opposed to just being constant sized, right? And it's assumed that all light nodes will have to download this. Again, the super light nodes can just download the Merkle root of these and not do data availability checks and just trust an honest majority. But the secure light clients that do data availability checks will need to download this 4 square root of n commitment. Okay, great. So now that we have this, how many shares does an attacker have to hide to prevent someone from reconstructing the original data and therefore the full block, approximately?
Okay, so approximately it will be, so to reconstruct everything, we need approximately n, right? Of those little shares.
Yeah, that's true. Yeah, to reconstruct everything, you need around n. Yeah, where n is the block size.
Right. So I will need to hide 3n. Right. Oh wait, or do I need to hide n?
You need to hide n.
So n is sufficient.
I need
to hide more than 3n.
N is confusing. We can use ratios, right? Here the attacker has to hide half plus 1, right?
Yes. Here they need to hide 3/4 plus 1, right? Or like 3/4 plus
They don't have to hide 3/4. They have to hide. Let me draw the rectangle in red. They have to hide this much, right? So it's 1/4 plus 1.
Oh yes, that's
right?
correct. Yes.
Okay, so we can see is that if they hide, let's say this is 8, right? If they hide 5 from this row, you can't reconstruct the row. If they hide 5 from this row, you can't reconstruct the row, and so on for the columns, right? But if they didn't hide these, if they left, they left you a bit here, if they revealed this one, then you could compute the whole column, and then from that, then you can compute the rest one by one, right? So they kind of have to hide this. For a large enough number now, if you have a light node and then it starts, it starts randomly sampling here. For each round, we'll do the same as before. So here's round 1, what's the probability that a light node has been tricked, that the data is available but it's not?
It's 1/4, right?
A
Is it
light node
3/4?
will get tricked if it lands on something
Yes,
that's being
it is 3/4.
disclosed.
Yeah, it's 3/4.
So
Yes,
yeah, it's going to be 3/4. So our round 2 tries to sample again. What's the probability now?
9/16.
Yeah, 9/16, right? So so you keep going, right? So we see it doesn't decrease as sharply as the previous time, but it does still decrease exponentially, which is good. So you need to do more rounds of sampling to get the same guarantees, but it means you get a better guarantee elsewhere. So what's a better guarantee elsewhere? If we have to prove that the whole thing is erasure coded incorrectly, note that we only have to prove that a single erasure coding computation was done incorrectly, right? Which means a fraud proof is now a single row or a single column in size, right?
Yeah.
Do we agree?
Which is just square root. Yep.
Yeah. So now the fraud proof would be 2 square root of n, as opposed to being n with like the size of the original data, right? So now we'll write that out. So fraud proof is big O of square root n, where n is our block size. Right over here, up top, the naive scheme, the fraud proof is big O of n. Right. So this is kind of where we see the amazing thing is that we now have a fraud proof that's sublinear in size, and again, you only have to broadcast this fraud proof out if there's a fraud proof. In the happy case, the only thing you need to download is this commitment, and then a fixed number of samples, a fixed number of sampling, right? So this is kind of the nice property is that the number of samplings you have to do is fixed. It's not related to block size at all. So how would you increase? Let's say
while the number of samplings is not related to the size of the block, the light header now is
yes
is proportional to the square root, right? Yeah.
Yes, it does. So yeah, so one of the trade-offs is the light client headers are larger. So what this means is that if you want to kind of take full advantage of this, you would want to have a smaller number of headers, each of which have larger blocks, right? Which means that generally you'd want to have slightly longer block times than what you would see in some chains that have really, really fast block times, right? So instead of going for the 1 second block time, maybe you want to go for the 30-second block time, which will allow you to take more advantage of this factor here, right? So that's one potential downside, but the gains is that you have now secure light clients, which is amazing because as before, if the two choices are run a full node or have absolutely no security, that's not exactly a very good trade-off, especially if you want your base layer to process many transactions where a full node could be potentially expensive. Right. So now we have a third choice, which is you can run a light client with data availability proofs and do this with sublinear cost and still be pretty damn secure so long as there's one honest full node out there, which is a good choice. Right. No one's forced to use this, but now we have this option. Okay. So
it's one honest full node among our peers, right? So we need
no Eclipse attack, yeah. Yes. Which is Eclipse attacks are kind of hard to pull off, maybe not, but yeah. It's an assumption. So one thing we note is that if let's say we want to keep we have some security guarantee parameter, right? Security guarantee, right? So this is kind of like our guarantee that some fixed fraction of light nodes aren't going to get tricked, right? So this is going to be proportional to the number of rounds, right? Number of rounds that we set as a parameter times the number of nodes doing sampling, right? So as the number of nodes increases, then our security guarantee increases, right?
Right.
And as the number of rounds increases, so does our security guarantee, right?
Yeah. Also, I don't see your text until you
that's
committed.
Weird.
Cool.
There we
go. Now I can see it.
Okay. So we have some relationship here. So if we want to keep our security guarantee fixed and we keep the number of rounds fixed, right? Note that if we increase the number of nodes, right, we can actually increase the block size and have the same guarantees.
Right.
Right, so this is kind of an amazing property that, a regular, we're not talking about lazy ledger yet, but just this property, we have the amazing property that data availability checking allows you to have the same guarantees for larger blocks as you increase the number of nodes. Right, in a regular blockchain, if you execute all the transactions, then okay, you increase the number of nodes, you don't get more throughput, right? Like every node still has to validate every transaction. Here, every node doesn't fully check the entire block, right? Every light node only checks the only checks a fixed number of samples and download the square root stuff.
Mhm.
So as the number of nodes increases, we can have the same security for larger block size, which is a really nice property. Okay, so now kind of the two pieces of the puzzle are together. We have fraud proofs for any arbitrary state transition, and we have a way for light nodes to make sure the data is available so that fraud proofs can be constructed, right? So there's kind of one additional side caveat here before we start talking about lazy ledger, which is note that blockchains always need to check for data availability. You may have heard some people talk about, say, O of 1 blockchains, right, where instead of using fraud proofs, you use validity proofs, which is like a succinct cryptographic proof that some computation is valid. And you might think, well, the only reason you need this is for validity, for fraud proofs, right? You might say, if you have validity proofs, why do you care if the data is available or not, right? The transactions are valid. The miners can't create 1 billion coins.
Well, you
right?
know that some state is valid. It would be
Yeah,
nice to know what exactly is the state that is valid.
That is the problem, is that if a miner, or block producer in general, makes a new block but doesn't tell anyone what the new state is, like you have a state root but you don't know what the state is, essentially everyone's coins are burned. They can't move their coins because they don't know what the state is. So there is no such thing as an O of 1 blockchain. All blockchains, to be secure, need some way of solving data availability, and that means either have everyone run a full node and like actually try to fully download the block. It means making an honest majority assumption, at which point, what's the point of the validity proof if you're assuming that, or it means doing these data availability checks, right? So there's no such thing as an O of 1 blockchain.